Yes, so today basically I will discuss this linear response function. So, and maybe like next time I can discuss the non-linear response function if time permits and this slot is available. So basically, so this is our system. So this system. So and normally when we have this unperturbed Hamiltonian, suppose H0. So all these dynamical quantities they evolve in time with respect to this unperturbed Hamiltonian. But when we have an external perturbation, suppose some external force and which basically changes with the time. So we want to measure the response of the system in some dynamical observable with respect to time. And in today's lecture, basically, I will keep it up to the perturbation, which will be basically up to this first order only. So all the higher order perturbations are neglected in this case. Now all these this spectroscopic observables or any other thing. So it is easier to do these calculations in this Liouville space. So basically, I will first describe the basic of this Liouville operator and this Liouville equations, so that it is easier for you to connect with this linear response function. And I will basically derive this Liouville equation in the quantum mechanical frame. So suppose we have any quantity, suppose this A, this observable, which basically depends on this phase space Q and P. So in Heisenberg picture, basically we can write this rate of change of this A with respect to time. This and this on the right hand side we have basically this commutator of A and H. And according to this Liouville equations, this dA upon dt, this rate of change of A, is basically written as iota, and this L and A. And basically, if you solve these two equations, you will get this L when this Liouville operator this operates on A. So basically, it gives the commutator of H and A. So in this time dependent, if you solve this equation also, you can get this time dependent of this operator A of t basically as exponential of iota, this LT, and this A at 0. And in quantum mechanics, we know that any time dependent quantity, it can be expressed with a exponential on this left hand side with the plus sign, iota h t upon h cross, and exponential with a negative sign on this right hand side. So this response functions, these are very important in calculating some spectroscopic observables. We do it we do it in VSFG or any other spectroscopy. And in this case, suppose in this linear response function, so we have this dependence on this electric field. So these generally, if we have a this linear dependence on the electric field, then they can be expressed in terms of this linear response function. But there are some some exceptions to it. Suppose this VSFG and some other spectroscopic techniques also, in which the visible pulse is basically in the non-resonant part. In that case, even this dependence is non-linear, their response can be calculated in a linear response function. Yes. So one second. So now this Liouville operator it's a Hermitian operator. So basically you can prove this. So for Hermitian on the right hand side I've written this. So for Hermitian you can prove this. So this is some basic mathematics. Basically you can do that. So exponential of a Hermitian operator is basically unitary operator. So this exponential of this iota LT is basically an unitary time development operator. Now we have to suppose we are applying this external force or this perturbation on the system. So we want to measure the response of the system in terms of some quantities. Suppose here I have written this A. So basically, if you want to measure the time dependence of A, so you can do it in two ways. Either you can do it in the Schrodinger picture or this Heisenberg picture. So basically, in this Schrodinger picture, the wave function evolves in time, and in this Heisenberg picture, basically, this operator evolves in time. Basically, both these two are same. Only the difference is that this the difference is in the time evolution of the wave function and this operator. So now to measure any spectroscopy observable or any other quantities, it's not straightforward direct. So we measure this quantity with respect to change in the density operator. So what we do is we measure the change in the density operator, and then we connect the change in the density operator to the observable which we want to measure. So this is the this change in the density is written as this, which is given by this von Neumann equation. So which is basically a commutator of h rho and upon this iota h cross. And if you solve this previous equation which I was showing in the yes. So if you solve these two equations, then for this change in the density operator, you will get this equation minus iota h cross LT rho t. So this is just a basic mathematics. So even after arranging all those terms, you can get this equation. So if you have any doubt in like deriving this equation, I can discuss in detail personally. Okay. So then what we do is this total Hamiltonian. So basically, initially you have this unperturbed Hamiltonian, which is basically H0. So you have this thermal fluctuation, and all these quantities evolve in time, even if you don't have any this perturbation. So this H prime of t is basically this perturbation, which is in our control, or which we can say that this is a time dependence, and how much time we want to apply this external perturbation, which is basically in our hand. So now this perturbation, so basically we will derive this perturbation from t is equal to minus infinity. So basically at that time there is no perturbation, and at that moment only the Hamiltonian which is there is h equal to h0, and average of any quantities, suppose this b, so this is observable. So at equilibrium, so equilibrium is basically the time when there is no perturbation. So which is according to definition of any average quantity is defined as trace of b times rho of this equilibrium, and which is basically rho equilibrium is basically e exponential of minus beta h naught upon this trace. And in our case, if you normalize this, if you take this as n, only you have this numerator factor. Now this if you apply this perturbation, so this rho equilibrium, it will change to some rho which is function of t, which is basically it will be equal to some this rho equilibrium plus this delta function. This change in this equilibrium. And similarly, this perturbation, it will also basically change from L equilibrium to some function of L perturbation. So now we want to solve the response of the system when you apply this perturbation with respect to this density operator. So we if we go back, so this was the equation of this change in the density operator. So which is basically minus iota h cross this L and rho. So we write this equation minus iota L and this rho, and here L is total, and rho is also basically this total in this density operator, and we now break it into this L equilibrium plus L perturbation, and then similarly we also break it into rho equilibrium plus rho this then change in delta. Or if you break, or if you like expand these terms, you will get 4 terms, and basically the last term which is L perturbation and this change in this density, so which is basically very low, so we can neglect this quantity, this last one, and this first quantity, which basically this L equilibrium and this rho equilibrium. So at this rho equilibrium does not have any time dependence, so which so basically this change, it will be 0. So only now we have two terms, this L equilibrium and this delta rho, and then L perturbation and this then rho equilibrium. So now you can take this term to this side, and then you have this equation. Now this is a very in mathematics, this partial difference. Sorry, this if you solve this differential equation, we have this homogeneous differential equation. So there is a proper solution to it. So you can look at it. So basically, I have only written the after the derivation after this differential. So only one condition is that change in this density operator at t is equal to this minus infinity, it will be 0. So one condition you have to put, and then you can solve this differential equation. So now this change in this density operator is, now we have this del rho of t, and then minus infinity to t, and then the integration variable I have changed it. So basically this dt prime, and then this exponential, and then this inner term. So this differential equation, you can solve it this is mathematics kind of thing. So now after this this particular term which is inside this bracket, so it was initially, if you look at this one second. Yes. So this one, so these two equations are connected. So basically now we have this one. So this we can write it as a commutator of this h and rho. So here I have done in this similar fashion. So you can see this where you have minus iota L perturbation and then this rho equilibrium. So you can write it as this h commutator of h a, and then you have this iota h cross. Yeah, so here I have missed it, this iota h cross. So basically now you have this inside this bracket, so you have h prime, t prime, and then rho equilibrium. So, and now if you change this perturbation, then this one second. Yeah, so exponential of this minus iota t minus t prime L equilibrium, and then now we have this external force which we are applying, so which is basically f of t prime, and then a is basically at that moment when that this perturbation this starts happening. So this a of 0 is basically that. Now what we do, because when even if we do not apply this perturbation, still the quantities which are fluctuating due to this thermal fluctuation, it's still happening. So what we do is we basically change the frame of reference. So now we have this h0 plus h prime of t. So what we do is we go into the frame of reference in which the time evolution of those quantities which is happening due to this h of 0, we calculate in that particular frame. So whatever the whatever the quantities which are evolving in time, now we will have basically due to this h prime of t. Okay, so now if you leave this equation for the time being, and if you look at this, so expectation value or this average of B equilibrium, which is according to definition, is this trace of rho equilibrium and then this B. So this B, average value of B, which is basically this dependence on this density operator, which is basically equal to this sum of this equilibrium and then that particular change. So after that you can write this equation. So this particular change in the expectation value, which is basically the change which is basically due to the happening due to the change in the density operator. So this particular change is due to this particular change in the density operator. So now if you write this delta b of t, so according to this definition, which is basically b of delta rho t. Now we have derived this equation earlier in, if you look above, so which is basically this whole equation here. So we have to take the trace of b times this whole equation. So I have written it downwards. So this dt prime, and then in this integration from minus infinity to t, and then sum over all the force, like up to what time we are applying it, and then this trace of this b of 0. So basically here I have changed it. So b of 0, and then this a of dependence on this t minus t prime, and then rho equilibrium. So now you can see that in these three quantities, so basically they do not depend on this external perturbation at all. This rho equilibrium is basically due to this dependence on this h0 Hamiltonian, and then this b of 0 is the time this observable, and then this a also. Only this, the dependence which is coming from this external force, this is f of t prime. So
Ravi, no, Abhilash, go to the back.
Yeah,
so we need to understand this equation better way. This is crucial. Means here h prime t you divided into a0 f t prime. Now h prime t, what is the go the second and third line.
Okay, so basically
second to third line. No, from beginning.
Okay, here.
Second to third line, step by step. Yeah, more clear way. H prime t equal to a0 into ft prime.
Yes.
H prime t prime. What is H prime t prime?
So H prime is basically this only the
perturbation. Perturbation is the a0 and ft prime.
Yes. Minus a0 ft.
Minus a0 ft.
So, yeah. So f of t prime, and then this a of 0.
That we want to understand. Means go back. H prime is the perturbation. Suppose electric field means mu into.
Yeah. So H prime basically it can be any minus a of f of t. Yes, this a can be any quantity, like
at zero time. This is at zero time. Here a0 you have written.
A0 means at 0 time.
Okay.
So
and then you change the frame of reference. Basically,
yes, so,
you are using rotating frame here. Means the ft equal to rotating frame means you absorb that exponential i
L of
ilt. Okay.
So basically, instead of calculating in only the suppose this, we want to calculate this observable. So instead of calculating this also, we are calculating only the change which is basically happening due to the change in the density operator, not due to the rho equilibrium. So basically we are removing that dependence, because any quantity, even if you don't have this perturbation, this Hamiltonian perturbation, still the quantities due to the thermal fluctuations can it can move in time.
Then that will be f tilde, means you have to use different notation after changing the frame of reference.
No, actually, here, Abhilash, actually you don't need to change the frame of reference. Actually, what you are doing is that you are computing the B equilibrium, but the contribution of the perturbation, right?
Yes.
So just the delta B term, BT term, you are computing. You want to compute, not
only
not the B equilibrium average term.
Yes.
Yeah, so this is not the change of the frame of reference. Just you want to compute the term, the contribution from the perturbing term, perturbation term. You want to compute, right?
Yeah. So. So yeah. So basically, we are not changing.
Yes,
You want
means
to.
that part is you are changing this F0 to means
Uh,
Ft, that is not visible because
So
delta V, this is just delta V.
yes, all other terms are intact. So
Mm-hmm.
he is just computing the time dependent part of B, just
Yes,
not the equilibrium.
for the equilibrium. And I want to see one more thing here, that here e to the power I t minus t prime L equilibrium. I
this
think
one.
that is absorbed here in a t minus t prime in the last expression.
Yes. Yes. Yes.
From equation e to the power I minus I t minus t prime L equilibrium. This is
This.
absorbed in a t minus t prime. Means
Yes. So
here
this you
this
can.
your this frame of reference, I think it is changed here. Means for the a0 to a t minus t prime.
Yes. So
Yes, it
basically.
is just the Heisenberg representation of the
Heisenberg
equilibrium.
represent, means one can call it change of reference thing. Means,
Yes.
but he not on ft, means that you discussed here, that you written here. I think this is not on ft, but you applied it on a operator, a0 operator. Is that right?
One second. No.
Actually, Abhilash, can you show some pointers? Like Vanshida was talking about the
There is.
third equation from above, third equation and the last equation.
Yes.
So yeah. So in this equation, so you can see this pointer.
Yeah,
You can see.
So yeah. So if you like expand this term, so only one second. A second. So this equation you were asking, Vanchita.
This equation to last equation.
Oh, this equation
Yes,
to this.
yes. Means ft prime is intact, but you are absorbing this e to the power minus I t minus t L equilibrium. Means basically Heisenberg to means Schrodinger to Heisenberg
Schrodinger to
representation. Yes.
Heisenberg
Means what you call frame of, what you can call frame of reference change.
reference. Yes.
Means that is applied on a operator, not f operator. You have written.
Okay.
Okay, I think then it is.
So
Then
this actually I will have to check because this.
no, Abhilash, you are also correct. So you are both are confusing. You are also correct. Vanshida is talking about that the exponential minus I t minus t prime L equilibrium is operating on a0.
A0, yes.
Then it will become a t minus t prime.
Yes.
Yes.
Yeah. And a t prime is as like this. F t prime is f t prime. Okay. So just exponential operator is operating on a0, then it will become the a as a function of time t minus t prime.
It is important because means this step is very crucial. Means their linearity comes. Means you just take the here linearity comes. It is proportional to this f prime f t prime. You can see here this perturbation, this delta b.
Yes.
This effect means effect of this external perturbation come linearly, and and the proportionality factor is just this equilibrium commutator. Okay, equilibrium trace. Last equation.
Yes.
Means this is the main. Yes, for linear response, this is the crucial. Means this is the main crucial part.
Yes. So yeah. So basically, this frame of this change of reference, or instead of calculating in just in the terms of this total Hamiltonian or this we have like removed this dependence. So now basically we are calculating this change in B due to this change in the density operator. Now I think this frame of reference change, I meant that.
Yes. Okay, you go ahead.
So so now this, if you look at this equation, so which is basically inside the trace, so basically this equation, it has completely this independent of this perturbation. So only this zero, or this b of 0. So this time factor, which is basically up to what time we are applying this perturbation, so basically that factor is coming here. Otherwise all these row A and B are completely independent of this external perturbation. So now just for this function, so basically this, when we are applying any perturbation, so there is some response in the B. So that particular function is basically, they have called it as response function. So now changing this this variable, so t minus t prime, to basically tau. So we have expanded this response function further. So you can see, we can write this is basically b of 0, and then this you have this trace. So now expanding these terms, so you can you have these two terms now. And now using this cyclic rule of this commutator thing, so we can basically bring this a of this minus t to here, and then these two terms written here. Now this row equilibrium, so basically you can take it outside, and now we have basically dependence on this trace b of 0, and then this a of minus t. So from the definition what we have seen earlier, so any trace of any quantity at equilibrium, so basically this is basically called this equilibrium average. So this response function is this phi of AB is nothing but this equilibrium average of A of this minus t and then B of 0. So they have said that the fluctuation in this, I have written it, whether I don't know whether you can read it or not. So the fluctuation in this equilibrium, basically it governs the behavior of this average away from this equilibrium after this perturbation. Yes. So now this phi of AB. So if you change this variable inside this A of minus t or B of 0, you can write it in many other different ways based on this this variable. Yes. So yes. So this function with this phi of AB, and then this whole function is this linear response function. So I have read it till now only. So maybe in the next class I can discuss the non-linear response functions. So if you have any doubt, in the derivation part, then I can discuss it later. But if you have any doubt in the conceptual part in this linear response function, you can ask it now. Bansita, you have any doubt or you want to say anything?
No, this is yeah, this derivation is okay. And where this linearity comes?
So basically,
means where this approximate you made, means here in this page all is exact. Okay.
Yes. So this
And
the
the approximation
linearity is coming here. So if you look at this change in this density operator, so this part, this is the exponential dependence, and then this is the main part of the response function. So here you can see that this depends on the this first order of this perturbation L. So you don't have any square terms or any other terms here. So the linearity, basically after approximating all these four terms, if you like include this term, this order, then it will be difficult to write this response function. Otherwise, this linearity is coming from here.
And linearity coming from here, the approximation lies in the page before that, means yes. Here this approximation.
This one?
Due to this approximation, actually, you can this equation becomes linear. This dependence becomes linear.
Yes.
Okay.
Basically, you are neglecting the second order term here.
Yes, second order term.
Yes.
Here is the approximation. Otherwise,
Yes.
the next page,
So
everything is exact.
It just
linearity comes here at the second step.
Yes.
yeah.
Exactly. So we need to remember those where we made the approximation. Otherwise, we forget and use it in all the places. That's what I'm to stress.
Yeah.
Okay.
Yeah. So yeah.
Okay, you go ahead if no others.
Yes, maybe like if they have any doubt in derivation part, I can explain it later.
Abhilash,
Hmm.
what if you taken this first term, L equilibrium, rho equilibrium equal to 0?
Here? Yes, because this rho equilibrium, this does not have this time dependence. So this part is basically 0. Because the rho equilibrium is
So rho is equally changing.
yeah. So this term is the change in this density operator, and then this rho equilibrium is basically when you do not have any perturbation. That at that moment, so that is defined as this rho equilibrium. So yes, so maybe I just okay. Okay, Bansida. So should we stop?
Okay, this is I went to take some water. So
okay, so yeah, maybe this next time, in context of what like I'm doing as like in the project part, so where we are using this response function in calculating this spectroscopic observable. So I've discussed today this basic of this response function. So maybe next time, how we are using this response function to calculate some spectroscopic observable, I can discuss that, because that is also important, that how do we use this response functions.
yes, and this in that I can discuss that another point, this important point. You can again share the slide. That perturbation, that approximation, actually delta rho equal to yes in that point.
Yes.
There we can write it in terms of exponential, means we can approximate it in terms of exponentials, and from there we can show that if the commutator in the linear order, we can express it in terms of first order delta rho, second order delta rho, third order delta rho,
Okay.
Okay, in terms of, and there we can show that means as it is commutator. So first order commutator, it actually predominates when the process is Gaussian. Okay.
Okay.
So there we can get more general essence of this approximation. Here it seems that
This
that
process
earlier
is
question that when Ravi or no, the Himanshu presented that when delta rho is means when the perturbation is very large, okay, L perturb basically is very large, then we can't take this as zero, because when you are using laser,
this intensity of laser is very less, then only we can.
but when you are using this laser intensity is always very large,
Very high.
very high. So this approach means if we only remember this kind of thing, this L perturbed into delta rho tends to zero, then we cannot understand why this linearity is valid. Means if we express it in terms of commutator, then we can.
And this, what do you mean by this process is Gaussian? Like,
No, they are means I will show that derivation in detail.
Okay.
Means there, if you approximate this perturbation in exponential perturbation, then there if you divide, means if you make order by order, means lambda square, lambda cube. Okay, then first order is the cumulant term, and all higher order terms actually appears when the process deviates from Gaussian behavior. Okay, so this actually holds when the perturbation is Gaussian, means perturbation produce Gaussian fluctuation. Okay, so that is one point I wanted to.
Okay, so when this this fluctuation due to this perturbed Hamiltonian is Gaussian in nature, then and that deviation from Gaussian is which causes this higher order terms.
Yes. This causes this higher order. Then linear perturbation is, which deviation from linearity actually depends on means whether your perturbation produce some distribution which is different from Gaussian, means some asymmetric distribution like that. Okay. So there we can also, means if it deviates from Gaussian, there we can model it in terms of summation of different Gaussians. Okay. So we can model it in different well. It basically equilibrates. In one well, it have one Gaussian. In another well, it has different Gaussian. So we can model it like that. But by single perturbation, we can't explain that. Okay. So this linearity is very crucial to, means we are all doing this equilibrium MD simulation, but explaining the experiments where we create the non-equilibrium things. And why we can we can calculate those non-equilibrium properties, because as there are fluctuation is very random due to the central limit theorem, and there is almost, means all the processes does not deviate much from the Gaussian. Okay. So okay, means this is a nice connection that Ravi presented earlier, that yeah, this density matrix and this Himanshu presented this Fermi golden rule. Okay. And
Okay, so
Okay,
next time.
so then
Okay, so we can stop or
So I have just one question. This row has only time dependence, right? And can it also depend on some other variables?
like what?
Rho is a density, so it may have some coordinate difference.
Himanshu, speaker.
Oh. So it may also have some
Still, he did not switch on the speaker.
I think density is defined like for overall system. You know, maybe Bansida can answer that.
what is the question? Rho is?
He is asking that whether this density operator can depend on some other variables like a position or any other thing instead of just time.
Now, density in the Ravi discussion, Ravi already discussed that density operator means psi bracket and means we can write in terms of wave vector. Okay.
Oh, okay.
Wave vector, and this is how wave vector depends on time. Means your question is that how wave vector depends on time. Then density depends on the wave vector. So
Okay.
it depends exactly, means the same connections.
Okay. Okay, Bansida. So
Okay. So
okay. I'm leaving.